you a question. Like a professor should be really good at it. He's not so great. Yeah, I don't know why. It was a weird week. So, that's why well, it would be Alabama. Unless they lose good, man.
So, if you've got something hitting from the target,
I straight up was like, well, what's the other thing? Doesn't radiate isotropic? We don't have defined directivity in an object. So I'm just going to have to assume it radiates isotropic.
Class, let me just have your attention. So I have one last problem. I'm great at the test except for the last problem. And because they're two different exams, I had to sort out some way of being fair about some of the scaling because there were some mistakes made because one test had a bit harder of a problem than the other one with the waveguide just because of dimensions. Like the fourth motor is a TE30, not a TE. All right, so, but it was one of those things, a lot of people didn't take it out that far. And so I'm adjusting it. I'll have this thing scored and done in the next hour after class, and then if you want to get it, you can. I'll put your scores up online. Overall, I'm just telling you this. Bunch of people at the very high end, like no mistakes. But then there are people that honestly, it's like they haven't been in class all the time. I've never seen quite this discrepancy. It's pretty huge. And so I'll get these back to you, but I wanted to go over the exam, right? And I was a little concerned about how many people had problems with the first one, because that's a problem we went over several times. So I'm going to try to put it up here, if I can. Here. The way I created that exam, I looked at your old homeworks and quizzes, and I literally, some of those were old homework problems, without anything changing. So, bear with me for a second. radiations up to,
Yes.
I was doing this good chunk of the morning yesterday. Okay, can you get those lights in the back? Just hit the center one and then hit the two bottom ones, see if that'll be good. No, hit it again. Center one.
Huh.
Hit the center, yeah. And then hit one of the upper ones. Yeah, that's fine. All right, so. So this is the first problem. It has a short dipole, it has a 1 milliamp current, and a frequency of 300 megahertz. Now these are the correct answers for test A. And so I'm going to go through this with you to make sure nobody makes any other mistakes. This is the way, the proof of it, but here's the problem in a nutshell. And we have a short dipole. So if it's a short dipole, it has to be less than lambda over 10. In fact, it is. It's only lambda over really 20 is the length of this. So the first thing you're going to do is find radiation resistance here. Now, I have this there, but I'm going to put on radiation resistance is 80 pi squared, and it's the length of the antenna over lambda squared. Y'all agree with that? That's in ohms. That's the key. One of the common mistakes I saw is 73 ohms you spare. And I really was, because that is a half wave. So the very first thing you check is make sure you know what the length of the antenna is. Don't assume it's a half wave and don't assume it's short. Check. But it was stated that the length of this L was 0.05 lambda. For one of them, I forgot if it's the same one, but it's something like that. Now the frequency for this one, I gotta check on this one. This is 300 megahertz. So frequency is 300 megahertz. And that means lambda, and C over F, because it is free space, is 1 meter, right? That's the whole idea. So for this one, we've got the radiation resistance. The first thing we get is the power radiated. So P radiated, and this is always going to be the case, is going to be equal to, really, 1/2 the magnitude of the current squared times the radiation resistance. And that's going to be 1/2, and I is 1 milliamp here, I think. So it's 1/2 times 10 to the minus 3 squared times the radiation resistance, this. And that, I forgot exactly what it is. It's down here. 1.947, or 974, pardon. So this power radiated is small, and it's 9.87 times 10 to the minus 7. Okay, after you get the power radiated, now there are several ways you can get the next quantities. I asked for the E field. Some people, they just went right to the equation. This is absolutely fair. They said E is equal to J beta, right there. Then it's going to be times I times the length of the antenna. That's the length in meters, not in wavelengths, by the way, over 4 pi r. Now the phase you don't need here, because it's magnitude. And then it's going to be times the sine of theta. For this one, theta was, well, up here, was going to be 60 degrees. All right? And that will give you a correct value for the E field. And I just wanted the magnitude, and up there, magnitude of the E field is 2.721 microvolts. Now this is for, this has to do with this actual picture where R1 was 3,000 meters. So and it comes out to that. Another way to get it, and I put the gain of this antenna on the actual picture I had on the other page. So the gain was 1.5 sine squared, right? I want to make sure you know how to do both of these. Because I'm trying to make sure I feel very confident that that you understand this type of problem in its entirety without any confusion. First, you gotta figure out what kind of antenna. It's a short dipole. Probably on the final, it's a half wave or something like that, right? It's not gonna be the same, but you're gonna get a problem like this again. After that, to get the E field, this is one way. Another way you can get it is what? Well, if we're given the gain, and I'm big on doing this too, if I want the average power density, right, at a range, it's always going to be the transmitted power or radiated power, called P rad. Then it's over 4 pi r squared. Now that's the isotropic radiation, right? Remember how I tell you to do this? Then multiplied by gain, correct, class? Then by the gain. Well, for us, the gain is 1.5 sine squared. So the average power density there would be P rad. So it's 9.871, or 87 times 10 to the minus 7 over 4 pi. The range is 3,000, right? Squared. And then it would be times the sine squared of 60 degrees. And when you do that, you're going to get a value of 9.817 times 10 to the minus 15. So this is going to be an average power density incident on that target of 9.817. And that would be watts per meter squared. Now that power density, because it's in a far field, you can get the E field from this too. And that's equal to simply 1/2 magnitude of the E field squared over eta naught. Well, eta naught is equal to 120 pi. So you can go ahead and you can say E in magnitude is just equal to the square root of 2 eta naught times this power density, PF here. And in any case, you're going to get that E field. It's consistent. The only thing I saw was people using this. Some people just put down 0.05. They didn't multiply. I mean, the other one has a different lambda, but you got to realize ours is 1 meter wavelength, so 0.05 is 0.05, and the other one was 200 megahertz, so it was different. And the other test B. Let's see what else. All right, now once that's the average power density on the target, put out here. All right, so if I have the average power density right there, I hope you can see my little pointer. Now to find the total reflected power, it's just times sigma. Y'all follow me on this, class? It is, and so for sigma for this one, I think, well, I have 10 meters squared here, but it's actually, in this problem for A, it's 5 meters, or 5 square meters, right? So the only thing you're gonna do to get the reflected power is take this power density in C right here and multiply it by 5, and that would be this number. Y'all follow me? Are there any questions about this? There was a lot of kind of bizarre things I saw in this right here. Yeah.
So the target is a isotropic radiator?
No. Well, yes, it is. Remember with the radar equation, that sigma accounts for any variation in gain. It could be a function of angle. All right. But in this one, it's isotropic. It's like a sphere. So once you have that, now, and a lot of people put down lambda squared over 4 pi times a gain, and it came out of nowhere. This is the target striking. It's not the second antenna. So once that's the power that's reflected from it. Then after you have that reflected power, I'll do it right here. So here's the target, and now I've got a total power reflected here. So the power density on the next antenna from this, I didn't want the direct line of sight from the radar antenna to the second antenna. I just wanted to find out bistatically what happened. The power density, I'll call it PF2 on the second antenna. Well, that's going to be this, total power reflected. Then it's over 4 pi r squared. Now that's the power density that would be incident on the second antenna. Y'all agree with that? I don't know. See if I can show you. That's right here, E, the power density. Do y'all follow me on that, class? So that's, what is it, 1.943 times 10 to the minus 20. And that's watts per meter squared. Now, after that, you have to catch the power. Gotta figure out how much total power is gonna be really, it's really gonna be caught, I could use the word caught, but it's really going to be taken in by the second antenna. And that's gonna be, and this is gonna be the actual power, I think you call it power received in the book. That's gonna be lambda squared over 4 pi times the gain of the second antenna. Now that I gave you, there were two different ones. One was 10,000, the other was 1,000. I think for this one it's 1,000. Yeah, this one's 1,000. And then it's times this, times the average power, right there, power density right there. And that power received is 1.943 times 10 to the minus 20. And that's watts. Now after that, now you have to create, yes, sir?
You put the same number for the first one, is that the,
Oh, did I mess that up? Oh, power at a 10 and 2 is 2.44 times 10 to the minus 20, my bad. My bad. If you look there, I think it is right. Sorry about that. Yeah, now that's the total power received, but now you need to find the open circuit voltage, because that's the key to getting the last part of the problem. So then the open circuit, right, that's going to be the square root of 4 times the radiation resistance times this, P received. And that open circuit voltage, is 3.942 times 10 to the minus 9 volts. Now after you got that, then you actually just draw the circuit. I saw a lot of people that didn't draw the circuit on this one. They just assumed the open circuit. Well, I say that, I didn't do any statistics, but there was a lot of real confusion at this point. So then when you draw the circuit, you have the open circuit voltage here. That's this. Then you have to put the antenna's resistance, and if it had a reactive component, that in too. Like if it was an exact half-wave dipole, that would be 73.2 plus J42.5. Y'all hear me on this? Make sure you do, because you'll probably see this again on the final. Here it's just the radiation resistance. Now you attach your load, and for this one, it's 100 ohms. So now I just put 100 ohms on here. I'll call it R load, and I want to know this voltage. So that voltage at the load is simply going to be VOC. Then it's going to be times RL over RL right here plus R radiation. That in a nutshell are the steps. And we did this problem several times. I think, and I'm not sure when last time I did it, but y'all remember this problem in its entirety. It was a homework problem. We did several like this. It's real important that this kind of a problem is really done without any confusion, because some of the things coming up will require you to understand all aspects of this. Y'all follow me on this? You can't just remember the radar data. You can't just remember frisk. You have to understand the entirety of the process. All right, now these answers are for test A. And for test B, have that right here. It's basically the same problem. I think test B had 200 megahertz. Yeah, 10,000, you're right. So it's the same exact process we do for test 1. You'll notice the first sets of values are all the same, right? Because there's no difference in the power radiated. Right? The same length. The only difference was the frequency was 200 megahertz, and the gain on the second antenna was 10,000. So these are the values for that. I'll put them up there. And again, same exact process of what I put down. Y'all follow me on this? I was really concerned about the problems I saw with the power received, and really just a lot of people, for some reason, defaulted to a half-wave dipole, and I was trying to find out why they did that. I never figured it out. So please make sure you know the antenna type right off the bat. Okay, that's the first problem. Second problem, let's start with this test B on this one. Here, it's just a standard kind of, this is a chapter 6 problem. It was a homework problem, I believe, and a quiz problem. I don't know if you look back at your quizzes and see this. Y'all remember this problem? All right, the first thing I'm going to tell you, when you're given something like this, the frequency is always going to be the component inside the cosine argument that's multiplying t. That's omega. So omega is 4 pi times 10 to the 9th. The frequency would be that divided by 2 pi, or it's 2 times 10 to the 9th hertz. From there, everything falls in place. After that, because we have an epsilon relative and a sigma, now you have to get both the complex, or first you have to get the intrinsic impedance, and you have to get the actual gamma for that one. And if you look, it is a pretty good conductor, but it's not a perfect conductor in a sense. So I'm just going to put this down here. Most people did pretty well on this part, but I've got the answers here. Well, I take it back. I thought I had the other one for sure, but I'll put them up there. So if you look here, for the first part, the intrinsic impedance eta is just going to be square root of j omega mu over sigma plus j omega epsilon. In our case, it's going to be a square root of j times 4 pi times 10 to the 9th times, and this is 4 pi times 10 to the minus 7 over sigma. I think it was 5,000, right? Plus, this is plus j omega, which is 4 pi times 10 to the 7, or 10 to the 9th, pardon me, times epsilon relative is 72, and times epsilon naught, which is, you can take it as, if you want, it's 1 over 36 pi times 10 to the minus 9, or you can use 8.854 times 10 to the minus 12. Either one will get you there. When you do this, you're going to get this value here, this is for the second one, 1.77 at 45 degrees, about 45 degrees. So this is about 1.77 at 45 degrees ohms. Then you have to get gamma, and that's equal to the square root of j omega mu times sigma plus j omega epsilon. I've already put j omega up there, and I put sigma and epsilon, so I'll just put this down. It's going to be 1 plus j, and this is going to be times 6283, or 88. That's decimal points in the wrong spot. This should be 8,000. Angle 45 degrees. Now, the thing I'm going to let you know is here, because it's at 45 degrees, alpha equals beta is equal to 6283 for this one. How many had this test B? I know half the class did, but I'm just curious. All right, so I mean, these calculations we've done over and over again. Once you have that, the next thing I ask for is, so phase velocity, this is something I'm big on. So phase velocity is equal to omega over beta, right? A lot of people had phase velocity as something using the speed of light. And I didn't know why you were doing that, but, or wavelength they use the speed of light. Maybe I'm wrong about that. So for this one, it's going to be 4 pi times 10 to the 9th over beta, which is 6283. And the phase velocity on this one is 2 times 10 to the 6 meters per second. After that, I asked for wavelength, and this is the most common mistake on this one. People just put, for wavelength, they put c over f. If the phase velocity isn't c, you can't go there, all right? wavelength, the way you always get wavelength is, remember, beta times the wavelength is 2 pi radians. Do y'all remember that? That was the argument of the cosine that would cause it to be 1 period long. So then if you want the wavelength, you just take 2 pi over beta. Okay? How many did it that way? A lot of people, they defaulted to some odd formulas, but this is again a good conductor, so you can't assume speed of light. When that happens, you get 1 millimeter. And finally, for the H field, this is just something I'm sort of giving some of these to you just to make sure. If you know them, it's a breeze. You know, if you've done a lot of problems. But to get the H field, in this magnitude the E field, it would just be E over eta, right? If you just wanted magnitude. So I wanted the vector form. This is going to be the actual magnitude. Y'all agree with that? So what's the E field? Alright, take a look at that. That coefficient of the E equals 5. Just the magnitude is just 5. Y'all follow me? So when you get the phasor form, I'm going to spend just a second on this to make sure it's on notes. I was very lenient in the way I graded this. A lot of people just gave me magnitude. So the phasor form of H, right here, can be gotten by saying you can take 1 over eta, AP cross E. Y'all agree with that? Now if we put E in terms of a phasor, let's take a look at this for a second. What would it be? I'm going to erase this. I was very lenient here. There were all sorts of weird things. I saw cosine notation in there. I saw just about everything I didn't want to see, but I was lenient. I looked at the magnitude. So first, for the magnitude, can I take this? Let's put it this way. First, what is the direction of propagation? Just by looking at that. Everybody see it's in the positive z direction? Yeah. All right. So it's easy. You didn't have to do it this way. After that, we've got eta, right? Eta was what, 1.77 e to the j, and it could be pi over 4 radians, right, ohms, or 45 degrees. Do you all agree with that? Right. Then I need the E field in phasor form, if I want to do it this way. So the E field would be 5, right? Then it would be E to the minus alpha, right, which is minus what? Minus 68, 60, what is it? Something. What is that? 6283, pardon me. Tell you what, we're just going to leave it as alpha z. Alpha equals beta equals 6283 for this one. You leave it there, that's a real number, right? Now, then you have to do what? It's going to be e to the minus j beta. What's beta in this one? Same thing, right? Right there. Beta z in what direction? AX. This is consistent with Whitworth's book. I didn't try to do anything clever here and try to, make it go nuts with it. So, if it's propagating in z or minus x, it can do what? If that's the E field in volts per meter, then I can come over here and I can say that my H field is equal to 1 over 1.77. And then it's going to be e to the j pi over 4. Then I have a unit vector in the direction of propagation, az, crossed into the E field, which is 5, e to the minus alpha z, e to the minus j beta z. And this then would be an amps per meter. So when we do this, we're going to have a magnitude of 5 over 1.77. Then we're going to have e to the minus alpha z. And after that, this e to the j pi over 4, when it comes upstairs, it's going to be e to the minus j pi over 4. So it'll be e to the minus j, and it'll be beta z plus pi over 4. And when I take az crossed into ax, then I'm going to get ay. And that's what I was looking for, something like that. You all with me? Now, a lot of people didn't bother with that, they just got, and I gave you full credit, you got the right magnitude, I was just checking boxes here. But make sure you know how to do this for the final, you're gonna get asked this. Now you know. Alright, and that was the problem in a nutshell. I don't even know if I put the phasor form down. I didn't, I think because I got frustrated with the amount of people that I just didn't, they didn't bother with. Now some did, and I appreciate it. So the next part of this one is simply, this is right off the quiz. I don't know if you realize it, but this is the quiz that you took some time ago. After that, they asked for nothing more. I just asked for the E field and H field. So, and this is just the standard form, average power density right here for a plane wave, 1/2 magnitude of E squared over eta. It's that simple, and magnitude of H is equal to really E over eta, magnitude of eta. So for this one, you could say E is just equal to the square root of 2 pi, or 2 times eta, or eta not in this case, times Pn, and once you have that, you can get the H field. I think the answers are in there. But do you all remember that one? Everybody? If you've been coming to class, this should have been an automatic in terms of what you were expecting. The last one is the one I warned you about you were gonna get. I don't know if you saw that coming, but that was in class, the last, just before the test. Do you all remember this? Now, I was happy to say that most people did okay. Right? But I'm just gonna, maybe I'll just talk my way through it. Let's start with the first one. Just by inspection, just by looking at that, what's the direction of propagation? You all see it's negative x? How many see that? All right. You get it by looking at the coefficient, or the exponential, e to the j, beta, whatever it is. If it's got a plus j, it's going in the opposite direction. X tells you the direction. Y'all follow me. Now please, there were people that missed this and kind of bothered me. After that, what about the second one? Positive y. Y'all follow me? Everybody on this one? Okay. After I have that, well, I think this thing's got some things, this might be not the most recent copy. After that, to get E, when you assume free space, that's eta naught, the only thing you do is what? And I just care for the magnitude at that point. And just what? Multiply 10 by 120 pi by 377. That's it. All right? To get the frequency, and this is, people did, not all, but some people had trouble with this, and I thought I was pretty clear on this. How do you get that frequency if you're in free space? You've got beta, right? Now beta is equal to 1. Well, it's omega over c in free space, isn't it, class? Right? Really, it's omega times square root of mu epsilon if it's lossless. And in free space, it's omega over c. That means that's 2 pi f over c is beta, or I have beta times c over 2 pi is equal to f. And that's all you have to do with these. So for the first one, beta is 30. So I take 30 times c over 2 pi, and I get that frequency. The next one is 45. I just put 45 times c over 2 pi. Y'all with me on this one? Now the other test is about the same. I mean, I'm not sure all the difference. There's subtle differences, not much. I know, look at that. I think this is the first time I used this overhead. It's basically the same type of problem. Frequency, I think, was half for the first one. Frequency is 2 pi times 10 to the 9th radians. But for the second one, down here, I think this part is about the same. No, it's in the z direction. No, it is the same, I think. All right, but y'all follow me on this class? How this is? It wasn't meant to be hard. Just make sure you did your work and understood. Third is, I don't know why this one isn't filled in, but let me see if I got, if test B I put there.
Yes. The frequencies that you have on there on test B are, why are they different from the other one?
this? Which frequency? This is different. This is
Well,
4 pi
like
times 10 to the
The
9.
bottom part of that problem you would just run over.
It's gonna be beta times C over 2 pi. Aren't they the same?
I think we have different, that's the thing, different on test A and test B.
All right, I'll tell you what, I'll check it. This is the formula you use, and I can tell you, let's see. Oh, I think I know what happened. The first one was right, this one is not right. So this one is right, let me just put it. This will, wait a second, that's test B, hold on. Test A. Alright. This is right. This is the right answer. I think that's a typo on the other one. Okay, all right. I'm sorry. I've got, this stuff is on a different computer. I had it before class loaded. I thought I loaded everything into my folder, but I think I might have missed something. But I've got everything. I'll make sure the right one's up there. Can anybody check on that? I think that's exactly right. That should be. All right, now for the waveguide problem here, again, this is right off a quiz, and I think everybody was expecting this. So I'll just go through basically the steps of this. And the only thing that people messed up is that fourth mode. You only got a half point off at most. So first thing you have to do is find the cutoff frequencies, FC for the M and modes. And that's equal, since it's air-filled, it's C over 2, square root of M over A squared plus N over B squared. So the first lowest mode is an FC10, and that's a TE mode. And that really is just going to be equal to C over 2A. And I have these. Down. I have loaded these things, but I'm not sure if it hasn't. Didn't catch up. All right. Anyway, for this is the form. I think this is 7.5 times 10 to the 9th. You can check. I can do these things in a second for you. You all agree with that? Next mode is going to be the TE, and this is going to be the cutoff frequency for the 2.0 mode, and it's twice that, or 15 times 10 to the 9th hertz, or 15 gigahertz. Now after that, you have to take a look, and then for this one, it's going to be the TE FC01, I believe, and that is really going to be C over 2B. I forgot exactly what that is. yeah, that's about right, 16.67 gigahertz, right? And then for this one is going to be the, if you look at this is going to be, I think it's the PM, FC11 for the next one. You can check me on that. Y'all with me? Here, I'll do it for you real quick. Alright, so then, if I look at this and I take FC1 node, FC2 node, FC1, and so you can see the lowest are 7.5 gigahertz, 15 gigahertz, 16.67 gigahertz, and 18.28 gigahertz. That was for the first test. I'm going to just show you the other test. This one was, I think, 0.0665, right? I think so. But this one's a little different. Now when you take a look at this, first two are the same. Then 01 is 23. But if you look at this, see, this is 22.5 with the 3 ohm mode now. So if you missed it and you put 1 1 instead of 3 ohm mode, you lost half a point. That was it for that one. That was for, I think, test B, if I'm not mistaken. Then let's see what else. What mode will propagate class? Everybody got that one, just about. One or two people messed that up. It's going to be TE10. And how do you know that? Just for everybody's sake. You look at the frequency, the only frequency that is above the lowest cutoff, I mean, the only mode that is below the frequency of operation is the 1 ohm mode. Y'all follow me? And that's the way most work. So most people got that right. The characteristic impedance of the guide for that one, what you really need is to get the value K, right? And K is equal to the square root of 1 minus quantity FC10 over the actual operational frequency F. You gotta square that. And the operational frequency, 9? Yes. K for this one is 0.553. Now, I've got to put an 8 or not here that I haven't. And then I can go ahead and get my Z naught characteristic impedance, which is going to be simply 8 or not over K, because it's a TE1 on my, oh boy. What did I do wrong? See, it has all these built-in constants, and if you, it'll give you units and everything, but I use K all the time for meaning this. I don't use it for what they mean. All right, so that's the input impedance right here. And then for the reflection coefficient of the load on this one is 100 ohms. So I'll put it as RL for this one is 100. And reflection coefficient, I'm just going to use this symbol, is always going to be equal to the load impedance. I got the load impedance. And ZL is 100 ohm on this one, right? So it's the impedance you're going into minus the impedance you came from. Oops. Divided by the sum of the two. So that would be for the first one. Now for the second one, you're going to get about 0.54 or something. And I tell you because the actual characteristic impedance is different. I mean, the value of K is different, right there. But we'll talk about that in a second. So that would be for the first one, the values. And then what else? Reflection coefficient. Now, here's where you have to get voltage at the load. First, you need to get Z in to get that. And that was the problem a lot of people had. So we'll come down here. Now, when I take a look at this, I need beta. And beta, of course, is going to be equal to, and you can do it a few different ways. What is beta unguided? It's omega over C, isn't it, class? Right? And then it has to be multiplied by K, doesn't it, when you use it there? So you can take omega by C, and that's equal to 2 times pi times F. Divided by C. And then this has got to be multiplied by K because you're in the guide. So that would be beta of the guide. Then after that, I think it's 100 to do for this one, but I'm not absolutely sure. 104, sorry. No, just beta 2 pi over F over C is 180. Okay, now after that, go to the equation. I'd say Zn is equal to Z naught times ZL plus 1J times Z naught times the tangent of beta times L. Again, I have to define L in a second. And then it's divided by Z naught plus L in this one is 1.9 centimeters. So I got a Zn equal to that, and the magnitude of Zn is equal to that, and the argument Zn degrees. Now after that, your V source, I think it was 50 volts, wasn't it? Yeah. 50, so that means my Vn is going to be equal to Vs times Zn over Zn plus Rs, and Rs I think was 100, wasn't it?
Yeah.
So that means my Vn is equal to that. exp to the 1j times beta times L, and then it's going to be plus deflection coefficient times exp to the minus 1j times beta times L, and I get this, sorry, L's not that, my bad.
TL.
Oh, sorry, correct. Then, once I get that, the magnitude of this, and the argument. So that means voltage at the load is just going to be equal to V0 times 1 plus reflection coefficient, or magnitude-wise about 7.7. And the argument. And then for the current, now current's pretty easy on this one. That's just V of the load divided by R, right? Or Z load. And it's really, just take a look at that. Same angle, right? Then, last but not least, the power. Power of the load, you can say it's 1/2 times the magnitude of IL squared times ZL, because ZL is strip real, and that's about 300 milliwatts. Alright, so that's how you do that. The other one, the only thing that's changing is some of the values there, but it follows the same. Let me just finish this thing with the last problem and get done with it. So, and I'll put the values up there. For the last problem, the first part of it, this was the homework problem, whether you know that. I did change this cut frequency, but it was the homework problem. So for this one, this is the standard resistor, right? If you look at that, it's got 970 ohms of resistance. The first frequency is 10 megahertz here. That frequency is equal to the first break frequency here is actually equal to 1 over 2 pi RC, right? So F1 is 1 over 2 pi R times C. And then when you have that, you can see that C is equal to 1 over 2 pi R, this first frequency. I'll get that to you in a second. Once you have this, you know the self-resonant frequency is 1 over 2 pi square root of L times C. You just found C. You all remember doing this one? After that, the only thing I need to do is take 2 pi times the actual self-resonant frequency. Take that and square it, right? Then I have 1 over LC. Take 1 over this, and then divide it by C to get L. And so, for this one, I have R is 970, right? 9700, sorry, you're right. 9700, and that means C is equal to, based on this equation right here, 1 over 2 pi R. Times, I think it's 10 megahertz, but I'll call it F1. I'll put F1 here, equal 10 to the 7th, right? And that's the capacitance. I got a comment on this one when people made a mistake. So then to get the inductance, I'm going to this one, and I got to put F self-resonance for this one was equal to 2 gigahertz. So I come over here. I can say this is equal to 1 over and this is 3.86 times 10 to the minus 9. That was for, I guess it's test A, right? Or test, I'm not sure, but one of the same thing goes for the second test. The only thing that changes is gonna be those F1s and F2, all right? So there'll be slightly different values. Finally, the last part of this one, right here, when you have, I give you a diameter of 8.8121 millimeters, and so that's 8128 divided by 2 millimeters of radius. You'd have to divide by 2 to get the radius if you wanted to do it. Then you get RDC, I'll just tell you this, resistance here, DC resistance, is just going to be equal to the length over sigma times the cross-sectional area, which is pi radius of the wire, pi times radius of the wire squared. Right here, that would be DC, and you're plugging in the values. This is nothing tricky. For our AC, now you find out the skin depth here, it's going to be 1 over the square root of pi f mu sigma, and you're going to find out that's much, much less than the radius of the wire, so you default to the AC high frequency resistance. It's going to have the same L over sigma, but then this is going to be 2 pi radius of the wire times the skin depth for this one. I'll put these values up, I'm sorry I'm telling you so long, and I'll get this thing scored as fast as I can get, and put the grades up on. I apologize for not having this.
Say that they should be ready this afternoon. Come by your office.
I have a dental appointment at 3. I'm gonna go up there right now and just grade and hope